Hello and welcome back. The next module we'll be looking at is low power design. This is a very important topical area today. Increasingly, designers are trying to achieve goals of low power rather than performance at any cost. And you'll see why in the next few slides. What we're going to talk about is why power consumption is important in CMOS, how it's calculated, and what are some of the strategies to reduce power consumption. We'll see how energy is a consideration as well, total energy to perform a particular function. So these are the objectives that map onto what I was just saying. Let's get into why this is important. Well, the obvious one, of course, is battery-driven devices. You're all very used to having battery-driven devices, and you're all very used to how limited their lifetime is. A smartphone is targeted to last a day. So obviously maximizing battery life is valuable and has been for quite a while, and has led to successes of companies such as ARM, who've been very good at low power processor design. What you might not be as familiar with is the problems of cooling for higher performance chips that are not constrained by battery power supplies, such as they're wall plug powered. Typically you want a chip to operate in somewhere in the 85 to 105 degrees centigrade range. I'm not, of course, referring to the external environment. I'm not saying that take your chips to Venus and operate them there. What I'm saying is that when a high performance part is in your air conditioned home, the silicon in that high performance part is actually operating most probably about at 105 degrees C. And that is despite all those cooling fans and so on that you most probably have in your desktop computer. So why do we want to limit the chip to this junction temperature? Well, in general, the reliability of anything gets exponentially worse with temperature. There actually are transistor wear out mechanisms. Until recently, we didn't worry about these things, hot carrier injection and MBTI. But increasingly today we are worried about them. What they really are oxide failures in the oxide in the MOSFET, and they increase with time, and they increase faster at a higher temperature. In addition, transistor leakage, that is the DC power consumed in the circuit, we'll come back to this in a moment, gets worse with temperature. But practically, the issue that limits that wants you to control the temperatures inside chips are the on-off thermal cycles. As you're most probably aware, different materials expand at different rates when you heat them up and cool them down. This leads to stresses at the joins between those materials. So as a chip is turned on and turned off, or goes to low power mode or high power mode, everything's expanding in and around it, and particularly the solder joints are being stressed in different ways in each different thermal cycle. This leads to fatigue, much like when you take a piece of metal and keep bending it over and over again, it will eventually break. Well, so these failed solder joints and other connections are generally the limits on reliability on systems. Which, by the way, if your electronics is not working properly, a good whack on the side sometimes fixes it. And the reason for that is you're reseating a poorly seated connector, or possibly reseating a bad solder joint. At the same time, the cooling a chip can be expensive. If you want cheap plastic packaging, you're limited to a few watts. If you're willing to go to expensive ceramic packaging, you can go up to 100 watts, but at the expense of complex fans that are expensive themselves, that also take up a lot of volume. Heat pipes, for example, these are mechanisms that move heat within a system that are used in mobile devices. You need more and more of these features as the heat flux goes up. And above about 100 watts, you mostly need some form of liquid cooling, which is very expensive to include in a system. So given that we want to keep our chips to 105 degrees C in the case of desktop processors, the 85 degrees C is for memories, and we don't want to spend a lot of money cooling it, it constrains the amount of power we can consume in the chip, both at peak and on average. There are other issues as well. We have to get the power to the chip. Think about it. A 100-watt processor running from a 1-volt supply needs 100 amps. Do you happen to know what the service is in your house for connected to the electrical grid? It is most probably either a 100 amp or 200 amp service. If it's a smaller house, it's a 100 amp service. That is, to supply the power to your chip, you need as much copper as is in your fuse box, with those big thick copper bars in them, to supply the current at a low enough resistance. In addition, you have to get through a power supply, you have to do down conversion. This robs efficiency depending on the details, and the grid itself is inefficient as well. Finally, and of course not least, electronics is a significant portion of the world's total energy budget, and if we can reduce it, we can have some impact on global warming and other factors like that. So what this all adds up to is that today, power is the major constraint on system performance. It used to be the number of transistors per die times the clock frequency. This is why particularly about 10 years ago, there was a big race to keep adding more and more transistors and the clock at a faster and faster rate so you can get more performance out of the chip. Well, bang, we hit a power wall. And just adding transistors and upping the clock no longer could give us more performance because we had to turn it off in order to manage power consumption. And this continues to be a problem and gets a lot worse with future generations because the capacity of the chips keeps going up with Moore's law. So of course, in wireless systems, the system performance is limited by the amount of power that you can deliver and dissipate, because there's not a lot of room to get cooling air through a mobile device, and dissipate within the chip. Desktop systems could easily be a kilowatt, which would be impossible to air cool. You'd have to plumb it into your cold water inside your house in order to cool it. Even more routine chips, such as set-top boxes, as we add more features, go to Super HD modes and so on, could get expensive to cool. And finally, of course, as we move to the cloud, then the server farms and supercomputers that are the cloud infrastructure take an enormous amount of energy at each site. These are enormous sites often with cooling ponds and their own substation next to them, and so on. And today they take tens of kilowatts. In the future, they could take tens of megawatts, which would make it very difficult to even just supply this infrastructure that's needed. So for all these reasons, for all these applications, increasingly power is the constraint on system performance. That is, you keep adding performance till you run out of power, not transistors and clock frequency. This is colloquially termed in the industry as dark silicon. Now, what we're not talking about here is Darth Vader going around in our electronics doing evil deeds. What we're talking about here is that we have to turn silicon off in order to meet a power constraint. So here I've got a slide from ARM that illustrates this. In the 2008 processor at 45 nanometer, we could keep the whole chip on and meet most probably here for a mobile application processor 2 to 3 watt peak power. As we scale this down, we fit in more transistors. That's the area aspect here. We can run it a little bit faster or have longer critical paths. And the power scales down, power per transistor scales down somewhat, but not at a very fast rate. Thus, we're adding more features, we can go faster. The amount of the chip that can be turned on for the same power, this 45 nanometer node part, gets smaller and smaller. That is, the 11 nanometer node, to meet our 2 to 3 watt power constraint for a mobile application performer, only 10% of the chip can be on if it's designed in the same way as we designed the 45 nanometer part. Well, this of course is very perturbing. Why pay for this chip if you can't have it all This means you won't be able to play cruise the web while making a phone call, or play a game. That's the graphics is a big consumer power while at the full capacity of the system. You'd have to turn most of the silicon off. That is, the silicon is dark. And by the way, silicon does not emit light, so we don't mean dark literally. We just mean it is not on in order to meet a power constraint. That's power consumption. However, there's a good argument that what we really care about in measuring system efficiency, our design efficiency, is energy per operation. Of course, what I'm leading into in these set of slides is that because of the dark silicon problem, we have to avoid it by designing more efficient silicon. So the question is, how do we design and how do we measure getting more efficient, power efficient designs? Well, I would argue, many would, that for most applications, besides things like very low power ones like wristwatches, what you would really care about is energy per operation. Because for a variety of reasons. One is that obviously you can reduce power just by slowing it down, but that means it takes longer to complete an operation. You might not have met a performance requirement, and so on. I've illustrated this trade-off here at the bottom here. Let's say we have a 1 GOPS processor, 1 billion operations per second processor at 1 gigahertz, and it consumes about 1 watt. This is not a terribly power efficient processor, by the way. These numbers are just conveniently made up. Well, we could reduce that power to 0.1 watt by simply running at 100 megahertz instead. But then we get 0.1 GOPS of performance. Notice both of these have the same energy per operation, as it turns out to be 1 nanojoule per op. They both have the same energy efficiency. The right-hand design is not better than the left-hand design. It's just the same design operated differently. To get a better design, we want to get a better energy per operation. And that's how we measure the quality of our designs increasingly in this power-constrained world that silicon is increasingly turning into. So now let's look and calculate the power for a CMOS chip. There are 2 sources of power: static power, which is there whether the circuit is switching or not, and dynamic power when logic transitions are occurring. The static power is the leakage power from the drain to the source. And even when the gate is off, there is a DC current between the drain and the source because today's transistors are so small. It's impossible to physically completely turn off the channel into being strongly off. Now there is a trade-off between threshold voltage of the gate and the subthreshold current. If you don't understand threshold voltage, that's okay. But what this leads to is you can actually have some cells that are fast with a low threshold voltage, and some cells that are slow but have lower leakage. And sometimes, increasingly, libraries have both types of cells in them, the idea being that you use the low leakage cells outside the critical path. You might recall the critical path from the timing notes is the slowest path in the design. In logic, however, the majority of the power is dynamic power, that is when logic transitions are occurring. Small amount of this is the through current when both the NFETs and PFETs are on, but most of it is toggling power when the output node changes logic state. And this is what we'll look at on the next slide. So here I have 2 inverters in series, and I want to calculate the power dissipated due to switching at that node here that I'm pointing at. If that is not toggling, there is no dynamic power being dissipated. There's only static power. Now you might recall the inverter is a PFET up top and an NFET on the bottom, and I've modeled those very approximately here as resistors. And in fact, when they're on, you can think of them as nonlinear resistors. And the switching, one is the PFET is turned on to pull this node up, the NFET is turned on to pull this node down. The load looking in to this inverter on the right looks like a capacitor. A CMOS gate has no current between the gate and the drain, the source. What you see looking into the gate is a capacitor. So the node is capacitive. Now, when the node switches, power is dissipated in these nonlinear resistors. Right? Just like power is dissipated in a heating element when you run current through it. And that is the loss mechanism. That's where the power ends up as heat being dissipated in these nonlinear resistors that I'm using to approximate the NFET and PFET. But there's two ways to calculate the power that's dissipating in this realm. One way is to actually calculate the IR power drop in these. The other is to use the physics law of conservation of energy and realize that the potential energy stored onto the capacitor during a logic cycle is the same as the energy loss in these two resistors. So what we're going to do here is show you, at least outline, two different ways to calculate the power lost, the energy loss in this structure during a 0-1-0 cycle. Could also, of course, be a 1-0-1 cycle. The idea is a complete logic cycle, complete transition up and down again. Well, the easiest way to do that is to look at the potential energy argument. That is, we're storing charge on a capacitor and dumping it off. The energy of the charge that's stored in that capacitor is equal to the energy that's dissipated in these two resistors. How do we calculate this? Well, Q equals CV. Energy is Q times VDD. Move charge across the potential. That's how you store energy. So that means it's CVDD squared. Power is energy over time. T here is the how long it takes for a 0-1-0 cycle to complete, which is longer than the clock period. So what we'll do is convert that into 1 over T into N switch times F clock. These are defined on the next page. F clock, of course, is the clock frequency. N switch is the average number of cycles in which you get a complete 0-1-0 transition. For general logic, that is usually less than 50%. Alternatively, we could actually calculate the VI loss in the resistors. So let's look at the VI loss in the top resistor when we are charging up this node. So we're charging the node from 0 to VDD. This is the VI in that IV in that transistor. You integrate it over time. Place a time integral with a voltage integral as per the construction on the right hand side. Q equals CV. I is dQ by dt. So I is equal to C dV by dt. Substitute that for dt in this left hand equation. You get integral of the voltage transition times C dV. The integral of V dV, you might recall, is V squared over 2. So you get CV squared over 2, that's the power dissipated in charging it up. You also dissipate a power of CV squared over 2 discharging it, and thus you end up with the same equation that we got on the top here from the potential energy argument. So putting all this together, the power consumed in the CMOS module is the sum over all the nodes, N switch, F clock, V squared, C load. F is clock frequency, N switch again is the average percentage of clock periods in which the node does a complete toggle. C load is the capacitance of the node. We add to that this leakage power, which is the static power. This first term being the dynamic power. The question is that so most of this you can calculate from the layout of the circuit. Right? The layout of the circuit tells you what C load is at each node. You know the voltage, you know the clock frequency. So the question is, what is N switch? Unfortunately, that's a little harder to calculate. In fact, to get it accurate, you actually have to run a simulation. But let's look at some possible numbers here. For clock, N switch by definition is 100%. Every clock cycle you do a complete transition. For glitch-free logic, what is the maximum N switch can be? Remember, by glitch free I mean that during the clock period it doesn't go through intermediate transitions. Well, the maximum could be is 50%, because in any one clock cycle it can only go from 0 to 1 or 1 to 0 and not do both if it's glitch free. However, typically logic has an end switch much less than that, and to actually calculate this accurately you would need to actually extract end switch from the circuit simulator, and that's what's actually done in a power simulator, extracting end switch from a simulation of the circuit for each and every node and then using this equation. Now, before I was arguing that a more fundamental metric is energy to complete an operation, or possibly energy to complete a task, because that then obfuscates hide-offs that just trade power for time. So energy, of course, is the integral of power over time. We do this integral here, and you can rewrite it in this fashion. That is, we're now adding over all the clock cycles that we're calculating the energy for. End switch, F disappears because we're now adding over all the clock cycles, V squared 2 C load, plus leakage power times the time that we're doing the simulation. And again, the terms here come from the previous page, except now we're adding over all the cycles for which we're calculating the energy for. Now, in general, there is a speed-energy trade-off that looks like something like this. So you look at this equation on the previous page and go, well, there's an obvious strategy here. Wow, V squared. If I drop V, I'm going to have a big impact on energy and power consumption. And that, of course, is true. However, there's a very strong trade-off if you drop V, and that is you're increasing the logic delay. It increases slowly up to a point when the voltage VDD is around a bit over 2 times the threshold voltage of the transistors. Then it starts increasing very fast. Thus, operating at the lowest possible voltage down here somewhere might not be desirable because your processor will be very slow. And for computing and other applications, that sort of defeats the point. What's increasingly considered to do is to operate at the optimum energy delay product point on this curve, which of course is around the knee of the curve, actually a bit to the right of it. And people are talking about operating at this voltage a lot more in the future to get reasonable performance while trying to get reasonably low power consumption and in fact optimize their trade-off. This supply voltage works out to being somewhere around 600 to 800 millivolts, and we're slowly iterating towards designing systems that will operate at that voltage. So let's now look at the different scenarios in which you might want to control and reduce power consumption. And let's look at the system-wide strategies that are actually used to do this. So the first is when you're interested in performance, but you recognize that there are long periods of time which you don't need that peak performance. For example, you're sitting at your computer and all you're doing is typing in. Doesn't require a lot of compute performance to track a keyboard. Right? So what you can do here is reduce the speed and performance of the CPU while you're typing and get a power savings from that. So this is increasingly done. That is, reduce, let's say you have one of the cores on your processor that is monitoring the keyboard. Well, for that core, reduce VDD and reduce F clock to achieve adequate performance at a lower power level. This is called dynamic voltage frequency scaling. And it's already being done for CPUs and is increasingly being looked at for other applications. This requires more complex synthesis support. Your standard cell libraries have to be characterized all these different VDDs. And by the way, you can't change instantly between these states. if you suddenly have a big graphics computation hitting your core, you can't in one clock cycle go from zero point 0.4 volts, 100 megahertz to 1 volt, 1 gigahertz, because that will lead to a big spike in the power supply, which will cause problems in the power delivery system. Okay, let's say another scenario. We have the 4 cores in our processor, and all we're doing is typing. Why have the other 3 cores on at all? Just have on the core monitoring our current. Or, the example I use here, your application processor in your mobile smartphone has a camera decoder in it that turns the camera image into a JPEG compressed file. Well, if you're not taking photos, why should this even be on? So there's many scenarios when we actually want to completely turn off a unit. It was actually kind of difficult to turn it off by removing the power supply. We don't have good switches to do that. So instead what we do is turn off the clock. If we stop the clock to the units, the dynamic power goes to 0. We also lose all the state in those units, so you have to do a cold start when you apply the clock again. You can't assume it remembers where it finished last time, but that's okay for a JPEG decoder. That's no big deal at all. For a microprocessor, you just issue a reset. This is referred to as clock gating. And note, and I want to emphasize this, clock gating is done by the clock tree designer, not by the logic designer in the RTL. The system designer says to the clock tree designer, we want a gateable clock so that this JPEG unit can be turned off under system control. Please design the clock tree to enable that. And the clock tree is custom designed. As you, as the RTL designer, start willy-nilly sticking gates into your clock, logic gates into your clocks, you are really screwing up the skew calculations that the timing tools have to do to make sure the chip works. And you're quite likely to get a failed part as a result. Clock is golden, you can't play with it. Clock gating is valuable, the clock designer does the clock gating. In addition, at the same time, you might want to reduce leakage power, and we'll talk about this on the next page. Again, you can't turn the unit on back instantly. There actually needs to be some sort of stage turn on where it's turned on bits at a time by reapplying the clock a second at a time, again to prevent a big spike in the power supply. So if you're doing clock gating in an advanced high leakage process, you most probably also want to minimize the leakage power. The way this is done is to put what are called sleep transistors around your logic gates. These are transistors that have a high threshold voltage, thus when they're off have a low leakage. They'll throttle the current going into this gate. So even if these transistors in here have a low threshold voltage and a high leakage, it doesn't matter. Kirchhoff's current law will limit them to the current coming through these 2 outside transistors. So when you're in sleep mode, you turn both these transistors into a deep off state and minimize the leakage power in the circuit. And increasingly there are standard cells that come with these sleep transistors built into them. A third possible scenario is one where you want to minimize the energy per operation without a performance constraint. Or more precisely, the performance constraint is so low it effectively doesn't matter. Examples are hearing aids, wristwatches, increasingly long life battery operated sensors, or power harvesting sensors. In these scenarios, you want to operate as the lowest possible VDD at all. This is typically around 300 millivolts, which is below the threshold voltage of a transistor, and thus is referred to as sub-threshold. This means you have to have a cell library that's characterized at low VDD. And now, also, these low VDDs, the timing difference between Tmin and Tmax is so large it can actually be very hard to get timing convergence. In fact, preventing hold transitions in these sub-threshold logic families can be very difficult. For that reason, this still tends to be a somewhat specialized area, left to the few companies that build hearing aids, electronics, and wristwatch electronics. But increasingly, because of this view in the future, we're going to have sensors all over the place, to have a smart planet, to use IBM's term, then we might want to have increasingly people looking at this for long life, low activity sensors. So this 300 millivolt VDDs are coming around and they're here already wearing one possibly. But I must admit, most even low power designs are typically still done at about 0.6 volts or so for reasons of simplicity in the design process. Finally, the scenario that I talked about before, and that is you have a performance target and you want to minimize energy per operation or energy per task. This is actually typical of most microprocessors and frankly most specialized processors. We want performance. That's why we're going all this effort to write all this RTL and so on. So the question then becomes, how do you as a designer maintain a high performance, which means a reasonably high VDD, say 0.6, 0.8, or maybe 1 or 1.2 volts, and a reasonably high clock frequency, say 500 megahertz, 1 gigahertz, while minimizing the energy required to do a logic operation. What this comes down to is don't waste power. Think about what you're building from a power perspective and redo the design to emphasize those things that can be done power efficiently. Or take away things that are adding energy to the operations without adding utility to the function you're performing. Right? One way to think about this is to minimize the number of micro operations required to complete a task weighted by the energy per micro op. That's essentially what this dynamic power switching is here. Remember, by micro operation, I mean some atomic operations such as a multiply, a register store, a memory store, and so on. Well, this is actually what we're going to get back to in the second set of notes here, how to do this task, how to do efficient designs while achieving a high performance. So that leads us to the end of this submodule. I remind you about why we care about power consumption. We care about the battery life. We want to maximize the peak power so we can cool it cost effectively. And also we are worried about delivering the power or potentially all the way from the grid. Increasingly, we're worried about dark silicon. That is silicon we have to leave off because we can't dissipate we can't get rid of the heat required to have it all on at the same time. And a big focus of modern designs is achieving more energy efficiency, better energy efficiency better energy per operation, in order to reduce the amount of dark silicon that we have. And I remind you of the low power scenarios. If you have idle or near idle resources, you can use dynamic voltage and frequency scaling. Or if this resource can be completely turned off, you use clock gating, possibly with sleep transistors. If all you care about power and you're not performance constrained, you can bring the VDD all the way down as low as practical for your logic family and for the standard cell library you have and the tool flow you have. And increasingly people looking at doing this sub-threshold, that is under the threshold voltage of the transistor, around 300 millivolts. However, for an ASIC, the most common requirement is maintaining performance while minimizing power. This leads to really thinking about how do you maximize energy efficiency. That is, minimize the energy per operation, a reasonable clock frequency, and a reasonable VDD. And finally, I remind you of the key equation here. The power is the sum over all the nodes. The switching activity, percentage of cycles for a complete transition, times the clock frequency, times the supply voltage squared, times the capacitive for that node, plus the leakage power across the entire circuit. Well, thank you very much. In the next submodule, we'll talk about ways to achieve energy efficiency.